How we doing? Okay, great. So yes, today we are going to be cooking with WASM. My name is Judoflexchop. Real name is Ray, but you might have seen me as the developer behind Alkanes. I also heard some Frost talk around here. Who's my Frost guy? He likes Frost. Good. We have a Frost-based project in the works as well, called Subfrost. And we just recently launched the Oil AMM, which is the first AMM on alkanes. So I'm really excited about that. But I've been asked to come and talk about WASM specifically and how, and I try to do this in a way where it's like very actionable and keep it interactive. Let's, we're going to cover like just things you might have to encounter or do just to build a WASM program or put together a WASM runtime. And so for the purpose of demonstration, I actually built this presentation in WASM. This is, so we have Cooking with WASM by Flex. I try to get a picture of Snoop Dogg on there, but so it's hard to get it to build into WASM. Let's see. But the animation is much easier. So what is WebAssembly? A portable cross-platform binary instruction format for a stack-based VM. It's actually it's a pretty suitable format for an executable if you want to sandbox it or do anything with a custom runtime and really just want to control the things your program can do without having to run a whole LXD container or VM, which can be more overhead. Or if we had to run a VM for VirtualBox or something, every time we had to run an Alkanes transaction, Lucid have even more problems syncing up the indexer. But thankfully, we use WASM, which is a nice lightweight WASM interpreter that is made by Parity, actually. So WASM is interesting for a smart contract language because it actually was originally the Ethereum Foundation wanted WASM or some kind of WASM-based interpreter for their EVM, but WASM at that time back then was not really ready for that. There were things about fuel metering and other details that had to be figured out. But now we're in a better spot on the WASM side of things, so we can use it for smart contracts with certain caveats. So let's keep going through my WASM slideshow. So how do we use WASM? So to use WASM, you have to load it into a WASM interpreter of some kind. There's quite a few, actually. But the one we used with Metashrew, which is the indexer stack, it is a pure WASM environment for an indexer program for a meta protocol. Theoretically, you could index any meta protocol or do any kind of complex indexing on Bitcoin or anything that's Bitcoin compatible. I mean, if it looks, Dogecoin it even works. But for what we use for Metashrew is actually WASM Time, which is a project put forth by Bytecode Alliance. It's kind of like a successor to what in the back of the day we were using like Wasmer and stuff, which is base runtimes that were used actually to extend Postgres for the Graph protocol, which is kind of interesting because a lot of the ideas of Metashrew evolved from what they were doing to the Graph protocol for Ethereum. So Metashrew, I like to say, is very flexible, and we use a very modern, the build of WASM Time, which also has specific configuration for deterministic indexing, which is your primary concern if you're indexing something like alkanes, because even one fuel unit of compute cost could throw off your entire. You could end up minting a new alkane accidentally in some version of the indexer just from some memory address being even off by 1 byte. And if that happens, then your sequence numbers are off, and then people are mad. So we want to keep people happy, so we use WASM Time with a very specific configuration that actually is identical to the behavior of WASM, which was originally, that was built for smart contracts by Parity. So we kind of try to mirror that with WASM Time, but we get the benefit of the just-in-time compiler that from CraneLift, and that gives us a pretty good performance boost. And actually, in the early days, we were trying to figure out if WASM would even be performant enough to do something like indexing Bitcoin data at scale. Turns out it works pretty well. I think block times, we can still speed them up a little bit more, but there's other things we can do. But for now, Alkanes works. Everyone's able to run, I think, about 1 billion units of fuel in a block at max, and things are going smooth. So yes, let's talk about how to build one of these WASM programs for a custom runtime even. So we're starting with the Alkanes runtime. The Alkanes is notable because WASM, we use WASM, which again, built by Parity, but is interesting because it can actually build to WASM. So Alkanes runs for smart contracts will use the WASM runtime, which is the VM for WASM, which is built to a format which runs in WASM time in Metatrue. So you kind of have two layers of WASM where we not only get the deterministic properties of the indexers that we need and keep the WASM format, but we actually have a WASM interpreter within that environment which can securely evaluate smart contract state and otherwise process what are usually very short protocol messages, just with the size limits of op return. But in this case, it's very handy for just smart contracts in general. So we actually took that. We were lucky to leverage all the research and development that went into the Polkadot project and Substrate, which honestly helped me a lot when I was learning Rust and learning how to do this stuff. I think I studied Substrate more than anything else, as but the code quality is very strong, and actually taught me a lot about how to design some of these things. So, but anyway. The choice of the runtime is just an implementation detail. A WASM program should behave the same, regardless of the environment, if it's correct, if the runtime is correct, that is. But there are things that you have to watch out for, basically, when you are choosing a WASM runtime, because there's things like even a hash map. If you're compiling from Rust to a WASM program, the ordering of the way if you were going to enumerate the keys of a hash map, this is a specific problem you might encounter if you're doing things that really require strict deterministic behavior. A hash map will not have a consistent ordering if you try to enumerate its keys, unless because actually the hash function that comes in default in the WASM environment that Rust builds to can depend on the memory addresses. So you have to have a consistent memory layout, even just to be sure your hash maps are enumerated properly. And that's just one detail that you have to look out for. But there are ways to configure WASM time for that specific scenario, which we will dive into. So just to cover what a WASM runtime may look like. The alkane's runtime, I think we try to keep it pretty simple. We have in Rust, you might see something like this, where you use the WASM bindgen macros, where you can actually define a set of bindings in your Rust program just by declaring this block here. We are going to define imports that our WASM runtime are going to try to load and assign pointers to when it loads a WASM binary into the runtime. So just by declaring these, this will add imports. The strings will even appear in your binary. Where you have, in this case, we have bindings for storage. We have a way to log if you have log enabled. We can check balances of an alkane. We can request its operating context, which may include its own address and other the inputs that are being sent with the protocol message. And we can do, but all these functions basically cover the scope of all the things you can do in an alkane, and they're all defined in one file. You can, it's right here, alkanes rs. But so when you actually build one of these things, you either import a module that will declare these imports, or you will you can define them explicitly even in the function that you're evaluating. But otherwise, these functions have to be defined in the runtime for the WASM binary to load. So we can take a look at what that looks like. But let's see. Have a slide here just covering the actual primitives in WASM. When you're actually calling a function in WASM, you're only going to be able to interact with, or the host environment is only going to get one of the primitive types in WASM, which are the I32, I64, which is your unsigned integers, and then we have the floating point types, which can work also in a deterministic way with a specific configuration. But these are the types you're going to be working with. Very simple. There technically is a table type and a few other types, but the primitives you'll generally be working with are going to be pointer addresses a lot of the time. Just because if you're going to pass between the host environment of your WASM program and the actual WASM executable itself, you're going to be writing and reading to memory regions that are in the WASM region. So your host environment is likely going to request a pointer and then start reading from that pointer, or otherwise write to the pointer. And that's how you can write large regions of memory and pass information back and forth between a runtime and a WASM program. So to compile a WASM program, I prefer Rust ultimately. I tried working with assembly script for a while when in the early days of the meta protocol work I was doing. Started probably about a year and a half ago. I started working with these things really when BRC20 picked up. Built out MetaShrew as my idea of what would be a very universal way for anybody to write their own meta protocol. And took some time before it became like mature enough where that would strictly the best option you had. I think right now it's pretty good. So to actually compile one of these programs and like an indexer, you're going to be basically you're likely going to be using Rust. It's one of your better choices. But you target the WASM32 unknown target, and that is a WASM build that is going to make no assumptions about what's available in its runtime. It is going to build whether you supply your own bindings. So you can define whatever functions you want. There's no system calls that are enabled by default unless you add them to your runtime. But if you compile for this target with Rust, it's just a flag, is a hyphen target, WASM32 unknown, and if you build with that flag, you're going to be building a WASM binary, and that's kind of where you start. And so if you can build a WASM binary that may have no bindings, but you can still call its exports from a host environment in different ways, or even the Node.js WebAssembly object is one thing that you can do to invoke a WASM binary that maybe has no imports. But to make them do something interesting, we have to add some stuff to the runtime. So this is an example of a Rust build file, as the cargo.toml, which may target a WASM build, and you'll note that we have the crate type is this cdylib, rlib, and this just ensures that we have an actual WASM file as a build product of the running cargo build. And I have some other dependent. This is just an example. It's just a snippet from alkane's RS. Let's see. And then running the WASM test is probably the most important part, because even getting something off the ground can be unwieldy if it's something like a meta protocol. And the scope of testing a meta protocol, if you're trying to do it in any way that's manual and you don't have it factored out in the unit test, it's going to be hard to get that to work. So when you're designing a meta protocol, I think that probably what helped us get something like alkanes off the ground and actually work was just the way that we tested and the test harness that we made around the MetaShrew imports. So basically, instead of like in the previous slide, we have these imports that are defined, which maybe are introduced. Your runtime will try to find them defined in the binary that you're running. But in our case, we would just mock those. So we mock the entire environment of a single block and be able to simulate all the conditions and edge cases that we needed to cover something like alkanes, or even we now have inscriptions too on MetaShrew, which I just recently got done. But the way you do it is you just factor down and break down into smaller problems, and you just simulate the smallest possible examples of a single primitive or class of objects in your meta protocol and how they interact. And eventually you can get code coverage, and just breaking the problem down into smaller steps. The way we do that is with WASM bindgen CLI. It installs the WASM bindgen test runner, and that gives you a nice default Node.js object that is going to be run within cargo test, where you can basically test your entire meta protocol in a matter of 5 seconds, depending on how many tests you have. But this is how we got alkanes to work, because I think that the level of detail and precision that it requires to build a smart contract runtime as a meta protocol with like alkanes, it can be extreme unless you can factor it down and into a nice test suite like this. So just to discuss more other examples of runtimes you may define, and if you're working with meta protocols, or if you're working with smart contracts, or really any application that WASM could be applicable toward. MetaShrew itself, this is a very simple runtime that is defined for MetaShrew, and this is exactly these functions here. We have functions to get the size of the input, which it'd be a block in this case for a Bitcoin CDC pipeline. Then we have a function to load that input into a memory region. We have 2 functions for that deal with this problem, because just because we are dealing with the simple primitive types we have available in WASM, and we're really just working with pointers. So, and other than that, we just have a function to get a value from the key value database, and then we have a value to flush the entire set of CDC updates or key value pairs for the block in a single host call. And we just have another function for logging, which we also mock in our test runner, so we can actually get very descriptive and information when we're testing and logging a meta protocol. So that's the entire runtime for MetaShrew. It's really just get and set and load the block. And so, like, it's nothing else you really need to do if you're doing something like a meta protocol. But other WASM runtimes may be more involved. So, as I said, to use WASM time in a way that is deterministic, where you don't end up with issues with something like a hash map, or there's other things that can happen. But this is one way to go about it, where your memory layout will be very consistent, and you can reference this in the MetaTrue source code. Everything is open source that we've done, probably almost all of it for the last year or so. So yeah, all this stuff you can look up on the StandTrue Meta Protocol's GitHub. But we have full examples of how to make these WASM runtimes, how to declare macros to abstract your WASM programs, and this is probably the more critical snippet of code here. You can find this in the MetaTrue runtime crate. But this is how you make a WASM runtime, a WASM time instance, which is a WASM VM, and make it deterministic in a way that is very much sound. So I think that if you don't do this, you may have edge cases where your meta protocol fails to be a meta protocol because it can't be reproduced consistently. Because if that property doesn't hold, then it can't be a meta protocol. So for that to work, and if you're using WASM time, then these configuration options might help you. There's one for just configurations for crane lift, the just-in-time compiler, the way that SIMD is handled, which can is a way you can introduce parallelism in your WASM program. It's just available to the instruction set of the WASM runtime. And then just statics around just memory offsets are important, and just in the way that memory is written to, and just because there are often optimizations that you want to not make if you are doing something that has to be deterministic. Thankfully, WASM already has a lot of this stuff already done. It's designed for smart contracts. So if you're looking for an easy way to get started writing a smart contracts platform, WASM is a good way to do it. If you need more performance and you don't have to compile it to WASM or something, then WASM time is probably a very good choice. So this example might be kind of cut off, but in fact, my slideshow, so some visual here on what I'm doing here, but basically to define your WASM runtime, you're just going to you just declare what WASM module you're adding functions to, and you add that function. So we do that in WASM time via the linker object, but in different WASM APIs, you may do something that looks a little differently, but it effectively works the same in any VM that you're defining. You're just going to declare your set of functions in your WASM runtime and what they do, and you have a context that you're allowed to work with while you're in the body of that function, and you can interact with the runtime in any way you want. You have the freedom of the host environment to modify the environment of the WASM program, or interact with even asynchronously with other systems. Like one of the interesting things I've been looking into, kind of as I get closer to the MetaTrue V9, V9.1.0 is what we're working on. That's going to be the one where just make some performance enhancements where we can actually get a LRU cache, can speed things up and index faster. But after that, I'm actually looking at things just means to parallelize these WASM indexer programs. So that's done in the way I've actually put together a WASM runtime with hardware support, so you can actually have a GPU attached to your WASM runtime and ultimately extend your WASM machine with a pipeline. So if you want to look at anything like that, I have a branch of the MetaTrue project, which has it's called Vulkan, and that is actually has a WASM interpreter that can run on your GPU, I think, maybe, but we'll see. But the easier thing you can do is you can actually introduce multi-threading in a way that actually is standard, which is WASI threads. WASI threads, effectively, to implement it now, it just requires, it's kind of like code routines. You can implement multi-threading where you're instantiating a new WASM instance for every thread you're running, and it's just message passing after that. And so that is like possible to do, and something I'm looking at for just speed things up in alkanes. I think a few things I have to do just to get before I'm kind of out of ideas. So, but it should be fast enough for quite a while. And then here we go. So I actually have a sandbox that I wrote for an alkane where you can actually attack it, or at least in a pen testing sense. Like you can test what functions it has and see kind of its behavior without running it live. So that's where my alkane sandbox does. And this is also on reference in the GitHub. it's under the Altanac 7 GitHub. I'll post that. I don't know if we have a Discord or anything for this, but it's a good example of how to take a WASM binary and run it offline. So actually have a small demo of what the output looks like, but I think my scrolling, I had a pure WASM implementation of this scrolling on my code boxes here, but I do have syntax highlighting, so we can at least see a little bit. There is a nice example here, though, of what the output looks like for Alkane's inspector, and this is basically the output when you can run it. It's a tool called Diesel. You can it's capable of loading a WASM binary and runs it in a custom WASM runtime, which is built with WASM, and it's designed to attack the WASM, the Alkane, and figure out what it does. So we basically implement a runtime for that for this inspector function, which will intercept host calls and kind of detect the behavior of the Alkane the best it can. And it'll also iterate over the list of opcodes that we think the Alkane might have, and it'll factor out things that seem like unusual responses, so we may say that it is an implemented opcode. So in these different ways, you can reflect the behavior of a WASM program without actually running it in the live environment. So that's just some experiments that you can do with WASM if you're looking at Alkanes. I think for anybody looking at any hackathons for building Alkanes, I think now's a good time. We have Diesel Web is a part of this library here, but it's capable of building. You can build a Rust application, pure Rust front end, embed Diesel Web in there. It's built with no standard, so it runs your entire. It has wallet connect or connect wallet APIs. It has all the you can deploy Alkanes from the client. Using the library, and it kind of abstracts away a lot of the things that you have to deal with in Bitcoin if you're working with meta protocols. So this is kind of one of my later experiments, and just trying to build more tooling around this stuff. But yeah, this pen testing framework for Alkanes is built into the Diesel Web. So it's another WASM environment that builds to WASM that you can run right on the web page, and you can kind of reflect things about entities on the Alkane's meta protocol that requires some security analysis to really get details on, because you never know. Because I think in Ethereum you see EVM binaries all the time, from people doing MEV and trying to optimize blocks, and they'll find tricks, and they really often these binaries are not even written in Rust or Solidity or written in a high level language. They'll be written directly in assembly. So the only way to really get information on some of these binaries is to I lost it. Oh well. Yeah, so we're back from the beginning. Now we're fast forward. Actually, we're at the end. So the next slide is just a big thank you. So let's see. But before we get there, we can open it up for questions. But you.
Understand how much it's going to cost me in terms of gas, basically. Do I need to run an entire Alkane stack to test that, or is it something that I can tie into my test harness and have a tighter loop around my development?
So the answer is you can absolutely. You actually can do it. There's a view function defined in the Metashoe program for Alkanes, which is called simulate. Okay. This is a view function. So without even this is capable of running simulated transactions against Alkanes that will give you a exact figure on the fuel usage. But if you're you're running in the test harness and you're trying to simulate it offline, absolutely you can. Actually all the view functions that are in Alkane's RS, you can import directly into your test harness. So you can call it internal to your test framework. And actually, I think it's a lot better than I've worked with a lot of Solidity frameworks in the past. I think it's can get complex to test and iterate on smart contracts, but actually with Alkanes, you can test with the indexer itself.
It would be cool if I could say this function isn't allowed to consume more than X amount of fuel, and then if it does, it's test failure. That'd be awesome.
I think there should be a way to do that. You can reflect the actual the runtime that's being used, and you can set constraints, because the actual WASM time itself is capable of doing that. WASM is as well. So by reflecting those objects in the runtime, you can set constraints around fuel metering, and you can cause it to fail, and then do your normal asserts. Yeah. So definitely possible.
Yeah, I have a related question also on like fuel. Specifically, you mentioned like you have these different runtimes, but in essence, it is a consensus system. So all these different runtimes have to execute the same piece of code and come to consensus in roughly the same time. Is there any concerns around like DOS vectors where, especially in light of like, oh, some of them have access to a GPU. You mentioned like they can extend an access to a GPU where I run a program that normally would take 5 minutes on a GPU, but another indexer that doesn't have this GPU capability takes 20 minutes. The blocks keep on coming, so it's like DOS. It's denial. Like, is there some like? I'm trying to
Great
understand.
question. I think that DOS is the primary thing you have to solve when you're developing something that's running untrusted code and in a blockchain context. So the reason we have Fuel is I mean, the goal of alkanes and again, a lot of the examples with the Vulkan branch of Metashrew, the Diesel Inspector, these are all just crazy WASM experiments. But the answer to your question is that for alkanes to work, it must be able to be synced on conventional hardware. And that is the thing that makes Bitcoin work.
Yeah,
so
I know.
I
Like
think
we have all these SIG-op limits. Like we have the same thing on Bitcoin. That was
for
just kind of asking
for
what
sure. So
you scope kind of you have like a minimum viable like runtime.
So the canonical alkanes indexer it can be synced on conventional hardware. I think we've had it live since inauguration day actually. And it has been it still take about on my machine it takes 2 or 3 days to sync up. But I think that even on low end hardware it could still sync no problem. I think it has to, because otherwise it wouldn't be decentralized. Like but the GPU stuff is just ways that if we really wanted to and just go crazy, then it's possible. But and making it deterministic, I think is like my prototype. I don't know. I'd have to do serious testing to be able to say it's perfectly deterministic if I'm compiling to a format that's running. It's a WASM interpreter on a GPU. So I don't even know if it does build. But these are things that are possible. But anyway, for the alkanes indexer to work, we can't do stuff like that, unfortunately.
Yeah, okay.
It's not as it's not it's a little more boring, but it has to be.
Yeah.
Hey, is there a situation where you might want to actually have randomness, in the runtime, maybe for specific reasons?
Very good question. Is there more?
I'm sorry, no, that was the question.
That's the whole question. So, earlier in the presentation, actually, it is absolutely true that even if you compile with WASM32 unknown, it just depending on your choice of runtime, you can end up with edge cases where you have a little bit of randomness, and it's not good if that's the case. So, what we do is there is a way to configure WASM time, which uses the just-in-time compiler, and we use that just to optimize the speed of the indexer. For Metashrew, we configure it such that even the memory layout is consistent no matter what. And so in the default configuration of WASM time, you have a few vectors you have to consider if you're going to say that your WASM program is deterministic. Right. So with the configuration of the indexer, it's impossible. With the default configuration of WASM, which is the parity tech runtime we use for alkanes, it is not possible to have a random event, because otherwise and thankfully we've been able to leverage a lot of the research done by the parity team to make sure that's true, and so which is the VM we use for alkanes. The indexer itself, we have to just do some specific configuration, and it is deterministic, but we also get some optimizations.
I'd follow up. What if you actually want randomness? You want to be able to emulate some kind of verifiable random function or something like that. Is there ever a use case for that, or it doesn't?
The way I do it is I use the nonce or the block hash or something.
Okay.
And that's if you do, I mean, if it were possible to introduce entropy, then it would not be good. I think it'd be a lot of issues. But the block hash is fine, and it's not really random. But it's also the miners would have to I don't know, game the block to do it, which could happen. But and it's also a known vector on Ethereum because sorry.
No, I'm just listening. Yeah.
Oh, that's the block hash is basically the best way to do that, because you don't want to introduce entropy into the system. If there's an available source of entropy in a blockchain smart contract system, it can you'll lose you won't be able to reproduce the state of the network.
Yeah, agreed. You can emulate it with a nonce or some block number.
Yeah, nonce good. I think that's pretty much it.
Fair enough. Thanks.
Well, if we don't have any more questions, I guess we'll move on. Next panel, next talk. Thank you. That was awesome.